Okay, so for part 2 of 7-2 notes, I'm actually going to start with example 3 and then go back to example 2. Example 3 I think is a little bit more of an easy step to make, and then example 2. But anyway, find the moment of inertia for a uniform rod of length L and mass m, so much like we did for the last one, except this time the axis is perpendicular to the rod but passing through the center of mass. So for example 1, we found the moment of inertia when it was pivoted about the end point. This time we want to find the moment of inertia as it's pivoted about the center. Now if you look ahead, right, if you look at the moments of inertia that I gave you on the example page, we're going to see that we actually know what the end result is supposed to be. The end result that we're supposed to get if we choose to pivot around the center should be 1/12 ml squared. So let's see if we can actually then get that 1/12 ml squared there. Right, so let's see if we can accomplish that goal. So again, we're going to start this the same way we always will with these problems. So the moment of inertia equals the integral of r squared dm, right? The difference this time becomes we want to decide what our parameters are going to be. Now last time we went from 0 to L because we started at the pivot point and we went over to one end, right, which was L. In this case, if I choose the pivot point to be 0, right, so if I choose the center of the rod to be 0, then what would this end of the rod be, right? I'd be going off half the length of the rod but in the negative direction. So I'm going to call this negative L over 2, whereas this end would be obviously positive L over 2. Right? So all I did was I went half the length of the rod one way and half the length of the rod the other way. So I'm choosing the pivot point always to be 0, and then I'm defining my parameters based on that. So this time my parameters are going to be from L over 2, from negative L over 2 to positive L over 2. Right, so the beginning point and the ending point for my integral are going to be those two values. Other than that, this question looks almost identical to the first example that we did. So as in that first example, the most important part that we defined is dm, right? So to define dm, again, dm is representing the mass per strip, right? And the mass per strip would be taking the mass per length times the width of that strip, which is the change in my length, which is dr, right? Dr representing the change in our radius, our position. So it's a change in our length. So dm is m over L dr. So almost exactly again like what we saw last time. We're just going to plug in then our integral here. So the moment of inertia equals the integral from negative L over 2 to positive L over 2 of r squared, but again instead of dm it's going to be m over L dr. Right, so I'm substituting that in for dm. Once again, m over L are both constants, so my moment of inertia equals m over L out front, the integral from negative L over 2 to positive L over 2 of r squared dr. And just like last time, that r squared dr becomes r cubed over 3. Right, so at this point it's almost again identical still to what we've already seen, except those beginning and ending parameters. Right, so instead of plugging in L and 0, now I have to plug in L over 2 and negative L over 2 and see what happens. So the m over L is just going to hang out front for a second. I plug in L over 2 and then I need to cube it, right? So I need to cube it and then divide by 3. And then I'm going to plug in and subtract, so negative L over 2 cubed, not squared. Let's actually clean that up. There we go. So negative L over 2 cubed over 3. And then see what I get from this. So L over 2 cubed would be L cubed over 8, but then that's still over 3, right, which would really be L cubed over 24. Same thing with this. This would be negative L cubed over 8 divided by 3, so it would be negative L cubed over 24. So what we end up with then inside the bracket, inside the definite integral here, is L cubed over 24 plus L cubed over 24, because I have a subtraction and then a negative, right? So minus a negative becoming a positive there. So this is all within the bracket for the integral. I still have an m over L out front. So I've got m over L times L cubed plus L cubed, which is 2L cubed over 24, which would be L cubed over 12. And obviously, just like we saw before, one of the L's can cancel out. So by the time that I'm done with this, my moment of inertia, my I, equals ml squared over 12, or better yet, 1/12 ml squared That was supposed to be a 12. That's not a very good 12. 1/12 ml squared, which again is exactly what it was supposed to be based on our equation here. Right? So 1/12 ml squared is the correct integral for the moment of inertia of a rod that's pivoted about the center. Okay, so once again, it is very, very crucial that we understand this process, specifically, especially for a rod, but we'll see it for a circle here in the next example as well. Okay, so make sure you guys are getting comfortable doing this process. Again, you may have to just practice this a few times, so it wouldn't be a bad idea to just work through this example again on your own, and then check your notes if you feel like you get stuck. But very, very important for us to understand. So then let's try example 2, which is a non-linear, right? It's not just a rod, it's asking for a disk. And let's see if we can apply the same theorem, the same rule we've been using for the moment of inertia of a rod to that of a disk, right? So I am still going to start with that foundation, that definition for the moment of inertia. So the moment of inertia is the definite integral, and we'll worry about the parameters there in just a second, of r squared dm, right? So it is going to be this same relationship we've seen before. The difference is when we talk about a disk, so it does tell us it's a disk that's being pivoted through the center, right? So through the center of rotation here. So then if I think about the disk, it doesn't really make sense to take thin slices, right? Because if you do thin slices, the problem is each of those slices is going to have a different height, and therefore they're all going to have different portions of mass, and it just not a very practical way to break this up. So instead of taking thin slices of the disk, we're actually going to take these thin concentric circles. So I'm going to take still thin slices, if you will, but this time slices like maybe the slices of an onion or something, right? Taking these little rings out of the circle. And I know that is a terrible ring, but it's close enough to get the point across, hopefully. Right? So we're going to take these thin little slices out of the circle. Okay, so we're going to take all of those slices and then we're going to add them all up, and we're going to find our moment of inertia doing that. So if I think about that, okay, if I'm approaching it that way, then what are my parameters going to be? Well, if I start at the center of the circle, I'm starting at 0. Okay, so I'm going to start at 0. And then what's going to be the furthest I get away in terms of my slices? So as I work my way out, the furthest the slice is going to get away would be a distance of r, right, the radius of the circle. And notice I am going to use a capital R for the radius of the circle and a lowercase r for the specific position at which we're at. Okay, so there will be two different r's in this problem. Okay, so anyway, I'm taking my circle, I'm taking these thin little slices out of it, and then I'm going to add all of those up. Once again, the most important question in this example becomes, what does dm represent? Well, for the rod, dm represented the mass per strip, right? It represented how much mass was contained in this strip. And it really means the same thing for my circle, right? So I'll try to do a slightly better circle if I can, right? So here's my center, here's my slice that I'm taking out of it, and then keeping that as a thin slice there. I'm just going to keep it really thin, right? Okay, but anyway, the dm would represent how much mass is there in this ring of the circle, right? So dm is going to represent specifically how much mass is in that ring of the circle. Well, the easiest way to think about doing that is thinking about the area of that circle and then finding the mass per the area. So what I want you to do first is imagine we take that ring and we cut it up and we unroll it. So if you were to take that ring and you were to cut it and unroll it, wouldn't you be able to unroll it to where it's basically a rectangle or a parallelogram? Right? If you took that thin strip, that thin circle, and you unrolled it, it would basically be a thin rectangle, right? What would be the height of that rectangle? Well, the height would be whatever that change in width was, right? And what have we always been calling that change in width? Just like before, that change in width is going to be dr, right? So that height would be dr. What would be the length of that rectangle? Well, the length is going to be the distance all the way around that circle. So in other words, the circumference, which is 2 pi times r, right? And I am, notice, using a lowercase r because the circumference is going to depend on where the circle is. Right? We're not going to use a capital R because that would only be true for the outermost circle. So I'm going to use a lowercase r, and then we'll go from there. So then, if I want to find the mass per strip, right, I actually want, instead of the linear density like I've done for the rod, so for the rod I did mass per length, but because a disk has 2 dimensions, instead of just doing the mass per length, I actually want the mass per area of each strip. Right? So instead of just the change in length, I want the change in area of the strip. So I want the mass per area. So our area density, if you will, which sometimes they'll use as different symbols, I actually may not define it. We'll just call it lambda again here. But the mass per area of a circle would be the mass divided by what is the area of our circle. Well, the area of our full circle is pi times r squared. Right? So if I take the total mass divided by the total area of the circle, this would be the mass per area. So again, the benefit of this is if this is the uniform distribution of the whole circle, then if I take this times the area, that's going to tell me how much mass is within that little amount of area. So bringing these two facts together, how can I represent dm? Well, dm would be the mass per area, so the mass divided by pi r squared, times, again, the area of whatever little strip we're taking here, whatever little slice we're taking. And again, the area of that would be 2 pi r dr. So if we look at this, yes, we can clean it up a little bit. We do have to be careful, though. So the pi's obviously can cancel out. However, the r's cannot cancel out because, again, this r is representing the total radius of the circle. This r is representing whatever the specific position of that strip is. So we cannot cancel those out. So anyway, I end up with 2mr over capital R squared dr. So then if I substitute that into my integral, if I substitute that in, I get the moment of inertia equals the definite integral from 0 to r of r squared times, instead of dm, this whole mess here, right? So 2mr over r squared dr. Now we can do much like we did for the thin rods. We can look at what measurements are constants, and the mass of the circle, the mass of the disk, and the radius of the disk are both going to be constant values, right? So those two values I can actually factor out front, as well as taking that 2 out front. I can certainly do that too. Right, so I'm going to bring the 2, the mass, and the r squared out front. So then that leaves me with, from 0 to r, the definite integral of r cubed. I have r to the second and another r to the first, dr. So what does this end up being then? Well, if I do the integral of that r cubed, obviously it'd be r to the fourth divided by 4. And then we're doing the definite integral from 0 to r. Right, so 2m over r squared of the definite integral here from 0 to r. So just like we've done for our rod a few times now, we've got the 2m r squared hanging out front. I plug in r, this would be r to the fourth divided by 4. I plug in 0 and subtract that, that would be 0 to the fourth divided by 4, which obviously again is just 0. So this whole thing ends up being 2m over r squared, and then r to the fourth times r to the fourth over 4. That is an r to the fourth, by the way. And then simplifying this a little bit more, so 2 over 4 is obviously 1/2 m, and then r squared on bottom, r to the fourth on top becomes mr squared. So my final integral here, my final moment of inertia for a disk, for a uniform disk, ends up being 1/2 mr squared, which, if we happen to check our table of values, if you look for a disk or you look for a cylinder, it is 1/2 mr squared. So that confirms that we did in fact do this correctly. Right, so once again, question 2 here, example 2, much like examples 1 and 3, very, very important that you guys get comfortable with this process. I know it can be a little bit confusing, so if you are having trouble, particularly with defining dm, let me know. It does take a little bit of practice to do that, but the good news is once you see what dm represents, this becomes an easier and easier process as you go. Okay, so we'll wrap up the rest of this section, which gets a little bit easier, but still very important. But we'll wrap up the rest of the section in the third part of the video. I'll go ahead and start the second part of the video here.